I wrote out every expanded step for this example right here. And so I'm going to write less expanded steps as we work through these, but if I skip something, you're not sure how I got there, made a jump, please ask. We want to be really, really confident with these rules, because we're just going to be building on them. I squared equals negative 1. So whenever I see an I squared, I can cancel it out and put a negative 1 instead. But as you get more confident, you'll see, well, all an I squared does, since it is equal to negative 1, it basically flips the sign of anything it's multiplied to. Right? So whenever you see an I squared, you can basically cancel it out and throw a negative out front. Or if it was already negative, turn that into a positive. If it was negative, it becomes positive. If it's positive, it becomes negative. I squared just flips the sign of anything it's touching with multiplication. Now, if it's not touching anything else, if it's just a plain old I square, that doesn't mean it just cancels out and you leave nothing. You do have to put a 1, a negative 1, if there's nothing else there. Okay? It doesn't just poof disappear. Now what this means is 6 times negative 1, which is negative 6. But you can also see that step and just get in the habit of I squared means it flips the sign. It means times negative 1, which means flipping the sign. And if that were negative 6, it'd become a positive 6. Doing okay? Any confusions? Any steps I'm leaping over? The point out on this one, you have a choice. Now, so far, aside from we got some perfect squares and we got some things that can't be simplified. Here, 8 is not a perfect square, but it can be simplified. It's not a perfect square, but does it have a perfect square factor? No. 4 times 2, right? So we could simplify this as with 4 times 2, 2 times the square root of 2. And you can simplify that first and then multiply, or you can just go ahead and multiply and then simplify. Either direction, either thing will give you the same answer. Okay. So I'll show both. If we've got, we could simplify this as 2 times the square root of 2. Okay. Because that's 4 times 2. Okay. Root and release the 4. And the 2 stays trapped behind. Okay. And then times I, radical 3. And so our coefficients are 2 and I. And our radicals under 1/2, radical 6. And the other way to do it would be square root, leave it unsimplified. Then that would be I times the square root of 24. 24 is not a perfect square, but it's got perfect square factors. You can do 4 times 6. Okay. So that would be I square root of 4 square root of 6, which is 2I square root of 6. Root and release the 2, put it in front. So either way, you get the same answer. Whether you simplify everything completely first or go ahead and use your product rule and then simplify. A lot of times it's easier to simplify first because you're dealing with big numbers. It's easier to simplify. Here, it really was either way, the same difficulty level. The top one has an I, the bottom one doesn't. But now that that I is pulled out, I can use my quotient rule to put them under 1/2. simplify what's under the house. These both have i's. Now, with the product rule, if they both had i's, then 2 i's got pulled out, and by the product rule, we're multiplying, so I times I was I squared, and I squared became negative 1. Here, if your quotient rule, and both have i's, both are negative radicands, so both have i's, instead of I times I, which is I squared, which is negative 1, we have I divided by I, which is 1. Right, yeah. It just cancels out. Anything divided by itself equals 1. Yeah. So I times I is I squared, which becomes negative 1. I divided by I is just 1. Just cancels it out. Quotient rule, put it under one house, square root of 9. And so we get, so when you got 2 i's multiplied, you get a negative answer. When you got 2 i's divided, you get a positive answer, or it just cancels out, so it's a positive 1. Either way, though, you have a non-imaginary answer. You have just a pure real number. Double i's, whether multiplied or divide, cancel out. And you go back to real. Okay, so let's look at, these are sort of just how we manipulate, what the imaginary unit means, its definition, and how we manipulate it. So now let's look at what the bigger picture of complex numbers looks like. Okay. So for the interest of time, I went ahead and put this chart here so we just kind of talk through it instead of having to write it all out. But it gives you a good overview, understanding, and sort of study reference. So back on the handout here, we're going to look at that definition, but let's look at this box, this breakdown first. So all of the numbers in the world are complex numbers. Complex numbers can be written in this form. Every complex number, both real complex and non-real complex, can be written in this form. Real complex and non-real complex are all complex numbers. And they can be written in the form a plus bi. Now, a plus bi looks weird and messy. It's just a very formal way to write any number in the world. Now, a and b are real. They are real numbers. A is a pure real number, just an a, just a 7, just like a 7 or a negative 8 or whatever that real number is. And the second, and then it's added to an imaginary unit. And this imaginary unit is an I, that's what makes it imaginary, but b, its coefficient, is a real number. So for example, this might be 3 plus 4i. 3 is a pure real number, just 3. 4i is an imaginary unit. An I with a real coefficient, 4i, 4 is a real number, and it's the coefficient of I, so 4i becomes the imaginary unit, but it has a real coefficient. The definition of complex numbers here, I'm going to just add to this right here, the definition of complex numbers is a plus bi, and specifically sort of like simplifying all the wordiness, where a and b are real numbers. So there's that symbol again, remember of the set of real numbers. These are the numbers we've already been working with. That means, I'm going to go over, what those real numbers actually mean as compared to non-real. But a and b are just basically all those integers and fractions, anything, decimals, any kind of number we've been dealing with are a and b. A pure real, and then the coefficient of I. Those are real numbers, and I is the imaginary unit. And any number in the world can be written in this formal way, a plus bi, which has a real part, a pure real, and it has a pure imaginary, and they're added together. So if we look at just the real numbers down here, so that's all the numbers in the world, and the real numbers, the one we're mostly used to dealing with, are written like this, a plus bi, but b equals 0. Now if b equals 0, what happens to bi? If it has a coefficient of 0, Well, there's an I there, right? But it has a coefficient of 0. What if you had an x with a coefficient of 0? What does 0x look equal to? 0. Right. Just 0 times anything is 0. 0 times I is 0. If your b is 0, do you have an imaginary unit? No. Because if b is 0, then you have bi is 0i, which means there's no imaginary unit. This is a formal way to write what a real number is, which is the complex number form, a plus bi, but b is 0, which means you have no imaginary unit. You just have a real number. This is the formal way to write the complex numbers that we've already been working with. Now, these are all the real numbers we've been working with, which we normally just write as a, not with the bi, because bi equals 0 in this case. And these boxes inside of boxes means that every outside box includes every inside box plus something else. So our real numbers, we have the natural counting numbers, 1, 2, 3, 4, just the positive numbers starting with 1, counting numbers. If we include 0, then we say they're the whole numbers. Whole numbers are 0 plus all the natural numbers. If we also include the negative counting numbers, then we have integers. All of the positive, negative numbers, and 0 are our integers. Now, if we put an integer over another integer, then we get a ratio. In other words, a rational number. Okay? And that includes, rational numbers include all of these fractions. They might be proper or improper fractions. They might be positive or negative. It's just an integer over another integer is a rational number. Now, how does that include, let's say, is 5 a rational number? Can it be written as a ratio, as a fraction?
Yes.
How would we write it?
5.
Yeah. And that's not normally how we write 5. We don't have to put, but we can. We can write any whole number, any integer, as a rational number just by putting it over 1. If it can be written as a fraction, it is a rational number. That includes the negative ones too, so like negative 8 over 1. Okay. Now, rational numbers, other real numbers besides rational numbers are also irrational numbers. If a number cannot be irrational, it cannot be written as a fraction, then it is irrational. You look at your calculator, for example. If you put this in, let's say 2 divided by 9. There's a fraction 2/9. Is that a rational number? No. It's written as a ratio. If you can write it as a fraction, it's a rational number. And if you push enter, the calculator will do the division, and it's going to give you a decimal version of it. And you'll see this one is a repeating decimal. Any rational number, if you do the division, is going to be either a repeating or a terminating decimal. So, for example, like 1/2 is a terminating decimal. 2/9 is a repeating decimal. But either one of these can be written as a fraction, and so therefore they are rational. But any decimals you have that are not repeating and not terminating, they go on forever and ever and ever and ever and never repeat, never end, cannot be written as fractions. So, for example, square root of 2. Any non-perfect square, any square root of a non-perfect square is irrational. You don't even have to care what the radical. If it's not a perfect square, it's not rational. So if you put in square root of 2, of course, it's going to give you a decimal. And it might look like, oh, is there some repeating there? It might be sometimes repeating to has big chunks. You can't even see it on the calculator. But if it was a square root of a non-perfect square, you know, even though the calculator cuts it off, it will never end and it will never repeat. And if you try and write it as a fraction by going, math, enter, it can't do it. It's irrational. Can't be written as a fraction. Okay. So any non-perfect square root of a non-perfect square is irrational. Pi is a very famous irrational number. We use 3.14 when we do the math, but it really goes on forever and ever without repeating and without ever ending. And even though it's written here as with over 4, it's still not rational because it includes an irrational pi. In college algebra, you're going to be introduced to the E, which is approximately 2.7, but again, it's irrational, non-repeating, non-terminating. Very important number. It's another letter like I we never use as a variable because it's a constant. It has a meaning, just like pi is a constant. Okay. And all those together, rational and irrational numbers, make up our real numbers. Those are all real, which is just basically a plus bi, but b is 0, so it's just a real component. Now we're adding to those are complex numbers. These are also complex numbers, the non-real ones. The non-real numbers most simply include pure imaginaries. That's what we've just been playing with. Pure imaginary numbers are when you have your a plus bi, that's your complex number form, But A is 0. And what happens if A is 0? Yeah. All you have is a BI. Okay? It's still A plus BI, but if A is 0, all we're looking at is a BI. And so those are pure imaginary. And that's an I with a coefficient. And the coefficient is real. That's a real 3 that is the coefficient of I. Our imaginary unit is 3I and has a real B, coefficient of 3, and an I, making it the imaginary unit. This has a coefficient of -1. If it was just an I, it would have a coefficient of 1. That's a real coefficient, but plus an I. Okay? A coefficient might be positive or negative fractions. Coefficients might also be radicals. Now, if the coefficient's a radical, though, we actually write it behind the I, remember, not in front of it, but it's still a coefficient. Okay? Now, if we have both a real and a non-real component, we have both an A and a B, and neither A or B are 0, then we have what's called our non-real complex numbers. They include a perfectly real component, like 7, and an imaginary component, like 2I. And 7 and 2 are both real numbers, but 7 is a pure real, and 2I is an imaginary unit that has a real coefficient. So pure real, pure imaginary, non-real complex. And you always start with the pure real. In this case it's 7, in this case it's 5, in this case it's -1/2. And then you have a plus or a minus, and you have your imaginary unit. Here it's 2I, here it's -I radical 3, here it's 3/2 I. You treat the I like that, like it's an x, like it's a variable. So if it's a fraction, we pull that fraction out in front with the I right at the bar as if this were 3/2 x. Now, we can write any of these numbers in complex form, it's just that we have to put 0I. So that might look a little funny, but you have to be careful when you read your directions to the problems in my math lab or on the test, and make sure that if the direction says, write in this form, in the formal notation A plus BI, that you do so. So, for example, the number 7. Is that pure real, pure imaginary, or a non-real complex? Yeah, just pure real. We use this number 7 every day. But if we write it in this formal complex, it is a complex number though. It's a real complex, but we can write it in the formal complex number formation. So what is our A?
7.
That's our pure real. And what is our BI?
0.
Right, 0I. Which means this goes away, but if we're asked to write it in this form, we have to include it to show it's the full formal complex notation. And this is a pure real. It's a pure real or real complex. Okay? Which means it has an A only. Our B is 0, therefore our BI is 0. Well, if you had, say, -1/5 I. Is that a pure real, a pure imaginary, or a complex, non-real? Do you have an A?
Yes.
What's the A?
0.
0, exactly. So we have to write it, and then we can write a minus sign instead of plus, because this would be a -1/5 I. And that is a pure imaginary. But if we were asked to write it in the formal complex number notation, we would write it that way, but it's still a pure imaginary number, because our A component, our pure real, is 0. Pure imaginary complex, or so it's all complex, but you have the BI only. Now note that and this is going to come into play in a minute, if you had something like this, 2I/3, it's another pure imaginary. Okay. Note that you would write it as 0 plus, and go ahead and pull that out as a coefficient, a fraction coefficient, and make sure the I, not on the bottom, but is written right at the bar. Let's say we had -2/7 plus I radical 5. Pure real, pure imaginary, or non-real complex? because you have an A and you have a B, neither of which are 0. Okay? So this is a non-real number. These are all complex numbers. This one is non-real complex because it includes an imaginary unit. And it's not just pure imaginary because it also has a real component. It has an A and a B. Okay? Okay. And so this is a non-real complex. And it has the full A plus BI. It has a pure real component and it has an imaginary unit, both of them, so we consider it a non-real complex. And what is our A here? What is our A in this non-real complex? Right. And what is our B?
Is this square root of 5?
Yeah, radical 5. And when I ask for the B, I'm asking just for that real coefficient, not the I. Okay? This is A plus BI, but A and B are both real numbers. Here's the pure real is negative, or pure real A is negative 2/7, and our pure real, our coefficient of our imaginary unit is also a real number, which is radical 5. A real irrational, but it's still real. Just like here, our real numbers are A and B. Our A is 7 and our B is 0. Our A is 0, our B is negative 1/5. Our A is 0, our B is 2/3. If you're asking us A and B, those are the real numbers. The pure real and the coefficient. But the coefficient is part of the imaginary unit, so that makes that whole BI imaginary. Okay. All right. So now we are going to add, subtract, and multiply. Okay. Now, add, subtract, we're going to be working with not just the plain old imaginary units like we were just manipulating, but we're going to be working with full complex numbers. So always be careful doing this. Make sure you, if your directions say write them in A plus BI form, make sure you do. Even if you're missing an A or a B, you still have to put in the 0 as a placeholder. So add, subtract, complex numbers. Now, before I do this, let's look at it in terms of what our eyes are already comfortable seeing. Okay? For example, if you had 3 minus 5x plus negative 4 plus x. Let's take those same binomials, 3 minus 5x, and then we've got negative 4 plus x. This involves x's, no radicals here, no i's, just regular terms we're used to dealing with. What is the difference between these two problems?
That one's multiplied, this one's added.
Yeah. We're about to do the same rules we already know how to do. We're going to do with complex numbers instead of regular binomials. But the same problems that we have with regular numbers, you're going to have those same problems with complex numbers if you're not careful. The first problem we have is making sure we're doing the correct operation. You see two binomials and sometimes your brain immediately wants to FOIL them. These are added or subtracted. If you have two binomials and you have a plus or a minus in between them, then the first thing you do is see if there's anything to distribute. Then you can drop the parentheses and add like terms. If there's nothing between the two binomials, that means multiply, which means you FOIL. You get two completely different answers, two completely different operations. Okay? So this is addition and this is multiply. Okay? And that same mistake is made with what we're about to do. Otherwise, the rules are the same. Okay? So just be very aware of that. Now let's take, instead of doing regular terms, let's do 3 minus 5i. Okay? There's a complex number, an a plus bi. Notice how it looks like a binomial. Now, if it has an imaginary unit, it's not a polynomial. But we are going to treat it like we treat a binomial. Okay? We're going to be able to do the same multiplication, special products, adding and subtracting as if it were a binomial. Meaning when we're adding and subtracting, we can combine like terms. We treat I like an x and just combine the coefficients when we add and subtract. And when we multiply, we're going to FOIL and binomial squared and conjugates just like before. Okay? So even though it's not a binomial, because it's not technically a polynomial, we're going to treat it like one. So let's do 3 minus 5i is a complex number, plus negative 4 plus I. Notice I made it look just like this. It's just instead of x's, I put i's. Okay? Your eye wants to see these as a binomial, but just like you might make a mistake, as is often made a mistake of saying, oh, I'm going to FOIL this, or I'm going to add, just like you have to notice what's my operation here, you have to notice what's my operation here. This is adding, not FOILing. Therefore, see if is there anything we can distribute? There's nothing in front here, and this is a plus sign. If this was a minus sign, what would we have to do? Yeah, we'd have to distribute that negative sign, flip the signs. But if there's nothing to distribute, because it's addition, nothing to distribute, we drop the parentheses, and we combine like terms. Now, when we're doing regular terms with like x's, we usually put the x first and the constant second. With complex numbers, remember it's of this form, a plus bi, so we're going to put the real number component, the pure real first, and the imaginary unit second. And we're going to treat the imaginary unit as if it were a variable, and just combine it, when we're adding and subtracting, we're just combining its coefficients. Right. So we'll do the numbers first. Those are like terms. And then those are like terms. Our i's are like terms, so we just do, what is this? What is negative 5i plus I? Right, negative 4i. Because all we did, they're like terms, so we just did negative 5 plus positive 1 is negative 4. It's still an I. It's not an I squared. Okay, so you do these two, 4i minus 3 minus I. So here we have a pure imaginary minus a complex number. And then here, let's do a complex minus a complex. Either way, the first thing you should notice is these are not, this is not distributing. This is not 4i times 3 minus I. It's 4i minus 3 minus I. Check for that operation. You're not distributing. You're not FOILing here. In both cases, you're subtracting. Distribute anything you can distribute, then you can drop the parentheses and combine like terms.